Hello, this is Mr. McMurray, and we are here back to do one little bit more notes on work and sewing machines. So, a pretty easy day today. Real quickly, we talked about work input and work output. So, there's two types of work being done on any particular machine. There's the work that you put into it, which is like on the handle of the hammer, you put the force and the distance it, and there's the work that it puts out. This is the work input or win. This is the work output or watt. Watt. All right, anyhow, so what's next? All right, well, it would be ideal if I put a certain amount of work in and I get exactly the same amount of work over here, okay? Actually, it'd be nice if I put a little bit of work in and I got even more work out, but that's not possible, okay? You can't, there is no free lunch, there is no something for nothing. All right, the very best we could hope for is if I put a certain amount of work here, I get the same amount of work out here. I said if I move the handle 6 times as far and put a certain amount of force on it, this, in order to be the same amount of work, would have to, it only goes 1 inch, so it's only 1/6 as much, but to be the same amount of work, it would have to put 6 times as much force, okay? Well, unfortunately, that's not usually the way it is. That would be an ideal machine. An ideal machine means in a fantasy world and where everything is perfect, the work input would equal the work output. You would just get just as much work out as you put into it. Okay? But in fact, there is no such thing because some of the work I put into it is lost to friction between my hand rubbing on the handle, between the nail rubbing on the board, and between the nail maybe slipping or whatever here. So because of that, you always have the work input is always more than you actually get out of it. So if ideally I move this 6 inches, put a certain amount of force on it, it should move this 1 inch, and so I should get 6 times as much. I'm probably only get about 5 times as much work, or 5 point something, or maybe 4 something. But anyhow, it's still way more force than I could put on it. Okay, so it's still good. It's better. It's just not as good as I might hope for it to be. Okay. And like I said, usually it's because things slip or you lose friction and to heat and stuff like that. There's always all these parts are rubbing each other. Now, a hammer is pretty simple. If you have a more complicated machine with gears and stuff like that, then there's more surfaces hitting each other, and then there's just more friction, and so you're going to lose more of it. Okay. In some machines, it might be great if you get 40 to 50% of the work that you put into it out of it. Okay, but it would still make it better than not using the machine at all. All right, now, so there are two things that we use to measure how good the machine is, okay? First one is called MA, or mechanical advantage, okay? And this is kind of what we talked about here. When I pull this, I said if I put 6 inches, it goes up 1 inch, and because of friction, it's not 100%, so instead of 6 times as much force, maybe it puts 5 times as much force on it, okay? That would have a mechanical advantage of 5, okay? And the mechanical advantage of 5 is how many times the machine multiplies the effort force. So I put in one unit of force, it's going to put out 5, okay, if it had a mechanical advantage of 5, okay? You could also say how many times the machine multiplies the effort distance, if we're talking about like the broom, okay? I move the broom a certain amount, how much does it multiply that down here? Either way, it's how much it multiplies your force or how much it multiplies your distance, okay? And that is your mechanical advantage. Now, the calculation for that is we basically look at, well, how much force did it use? Well, you take the resistance force, how much force was applied on the object, and you divide it by the effort force, how much that I had to put in there. And so if it's 2 times as much, then I take this divided by that, I'm going to get 2. Okay, if it's 5 times as much, I'm going to get 5. So basically, we're measuring how much force it puts on the object compared to how much force you have to put into it. All right, and the bigger the number, the better. Now, if you had a mechanical advantage of less than 1, is that possible? Yes. Going back to the broom, we said the broom, you actually have to push harder up here than you would if you just did it with the whisk broom or pushed it down on the ground. Okay, of course, you also have to bend over, and it wouldn't cover as much distance. Okay, so if you have a machine that multiplies distance, you may actually get a mechanical advantage. If you do the force divided by the force, you may actually get a mechanical advantage of less than 1. Okay, and that means you're multiplying the distance, not the effort force. All right, but for most machines, usually the mechanical advantage is going to be more than one, and that's why we use it, because it actually multiplies our force or makes more force. All right. The other measure of how good a machine is how efficient is it, okay? Now, a light bulb's not a machine, but just to use it as an example, most light bulbs only use about 45 to 50% of the electricity goes through them to produce light, which is their main purpose, right? And they actually produce heat. This is true of the old kind that had the incandescent or had the wire in the middle that heats up. Okay, and that's one of the reasons people are going to fluorescent ones and the little curlicue bulbs and stuff like the LED lights, because they're more efficient. And so they don't waste nearly as much electricity. Now, the incandescent ones, a lot of times you could use it for a heat lamp and stuff because they gave off more heat than they did light. Okay, so that was good if you wanted the heat, but it's not good if you didn't need the heat and you're wasting a lot of energy on heat when you really want light. Okay, so that's important. But now, that's not a machine. That was more the power where we're talking about energy divided by time. Okay, if you remember, we talked about that earlier. But same thing goes for a machine. How much of the work do you put in gets put to work output, okay? And so the formula for that then, efficiency is the work output divided by the work input times 100, okay? Which one of these is always bigger? Well, we said the work input's always bigger because you lose some of the work you put in to friction, so this number is always smaller. So this is going to be less than 1, okay? For example, in our example with the hammer, I said I get 5 units of force out, I put 6 in. So 5 divided by 6 is 0.8333, I think. Okay, so 0.833 times 100 gives you 83%. Okay, so it's 83% efficient, and that's very good once again. Okay, so the closer you are to 100%, the more efficient it is. But like I said, a lot of times just being over 50 or 60% is good enough. Okay, it will definitely make it a lot easier, and it will be efficient enough that it's worth using the machine. Okay, so unless it was less than 1, there were basically, it would always almost, it has to be pretty low before it wouldn't help to use the machine. So it may not be 100%, but you want it to go closer. But efficiency is always less than 100%, because if the work output was equal to the work input, then you would have 100% efficiency. And once again, that's the ideal machine that we talked about earlier. It would be 100% efficient. But in the real world, that doesn't happen. You put work in, some of it gets lost to friction and heat and slipping and stuff like that, and you get less work output. And so usually it's going to be less than 100%. All right, and that is basically it for our notes. We're done with those, and so if you just answer the questions, and you will be done. Have a good day.